Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 5 of a unit electrostatic potential and capacitance. So let's begin with today's class. In today's class we are going to discuss about the equipotential surfaces. As its name says, it's an equipotential. That means a surface having the same potential. So let's look at definition of it. We can say that the locus of all points in a medium at which electric potential remains the same is called as an equipotential surfaces. That means let's say this is a point charge q, and with this point charge q I need to generate a some kind of locus so that surface of that locus can have a equal potential on throughout the surface. So what can I have? If you assume it correctly and you can feel it, it would be a sphere having a radius of r. So let's say at this point this is k q by r. At this location it is a sphere having a radius of r. At this location it can have a potential of k q by r. At this point having a voltage of kq by r. At this point voltage would be kq by r. So if you assume it, if you see it very carefully, then you came to know that throughout the sphere the potential is same, and as its potential is same, it can be considered as an equipotential surface. So so we generally equipotential means we are considering an equal potential. That means throughout the surface, if my potential is equal, I will say that yes, this is an equipotential surfaces for this object or this body. I hope these things are clear to you. Okay, let's see it graphically. That I want to plot equipotential surface for an isolated point charge. As we already discussed that this is a point charge q, and as it is a positive charge, direction of electric field is moving outward to the surfaces. So look at this is moving outward, this is moving outward, this is moving outward, this is moving outward, and this all are moving outward. Yes. So one thing, for positive point charge, direction of electric field is moving outward from the surface, that I know. Now one more very interesting point that I want to discuss is, let's say that this distance is r1. Suppose this distance, first of the circle, that is to the center, and second circle it is an r2. Yes. So if I want to write a value of potential at two location va and vb, what it would be? Yes, va would be is equals to k q divide by r1. Yes. And vb would be is equals to k q divide by r2. So these are two potentials. va it would be an kq by r1, and vb it would be an kq by r2. Is it clear up till now? Yes. Now by analytically, can you assume that which potential would be higher, va or vb? Which one is higher, va or vb? If you can see this very carefully, then you might know that r2 is greater than r1, and as both the potential having the same charge and k is always a constant, so as r2 is greater than r1, vb is less than va. Yes, vb is less than va. Are you sure with this? Are you? Yes. So if I am going to write a potential on this point, does it same? Does it a value of va only, or it would be indifferent? Yes, it is a same value. So this whole sphere, this all sphere can have a same as an va. Same way this complete sphere can have a potential as a vb. Same way, let's say I take third point, it's a c. then this complete dotted lines have a same potential. So what I need to discuss is that look at the direction of electric field. Can I say that direction of electric field is towards the decreasing potential? Now again look at this. This is VA, this is VB. I know that VA is greater than VB, and the electric field lines are moving from A to B, so I can say this, that direction of electric field is towards the decreasing potential. Yes, please remember this property of an equipotential surfaces. This will help us to calculate the numericals. Yes. Now, so this is equipotential surfaces for an isolated point charge. Now let's have some another situation in which, let's say this is a dipole, and one of the charge would be a positive, another charge would be a negative, and I want to plot an equipotential surfaces for the dipoles. So let's say if these are the dipole situation, their equipotential surfaces would look something like this, that uh, in between space would be having where there would be a no potential, but as soon as I'm moving from one point to the another point, I could have a circular fringe patterns, I can say circular patterns, to make an equipotential surfaces of dipole. Yes, I hope those things are clear. You can assume anyone as a positive, other would be a negative, and these are the equipotential surfaces for pair of similar point charges. Yes, similar point charges, I mean a charge having similar magnitude. When I consider a dipole, one of them would be a positive and other would be a negative, that you know. Yes, so now next, equipotential surfaces for different objects. That for the point charge, we already seen that for a point charge, spherical conductors are the equipotential surfaces, and it is the spheres that generate equipotential surfaces for a point charge. Now let's say my direction of electric field is something like this, and the electric field is parallel. Electric field is parallel. When electric fields will be parallel and the separation between two electric field lines are equal, I say that it is a uniform electric field. And for uniform electric field, equipotential surfaces are parallel plane. This kind of sheets could be considered as an equipotential surfaces. Yes, one more observation, that this is the direction of electric field. In this case, it is in positive x direction. This potential is V1, this potential is V2. Which one would be higher, V1 or V2? Which potential would be higher, V1 or V2? Yes, what we discussed in previous slide. What do we discuss? That direction of electric field is towards the decreasing potential. So V1 must be at a higher potential as compared to the V2. That's why only direction of electric field is in positive x direction. Yes, so V1 must be greater than V2. One more observation. If someone asked me that what would be the angle between equipotential surface and direction of electric field, what it would be? Shall I repeat? What would be the angle between equipotential surface and direction of electric field? As you can see, this is 90 degree, something like this. Yes, so angle between electric field and equipotential surface is 90 degree. This is the case for every object, for every situation. Yes, okay, let's move on. For a line distribution of the charge, do you know line distribution of charge? Yes, yes. For a line distribution of charge, equipotential surfaces are cylindrical. So you need to remember this. For a point charge, it would be a spheres. For a uniform electric field, equipotential surfaces are parallel planes. And for a line distribution of charge, equipotential surfaces are cylindrical surfaces. Yes, so this three you must remember. So let's look at certain questions or logical questions. So what the question asks, look at this. What they said is, on rotating a point charge having a charge q around a charge q in a circle of radius r, the work done will be. Can you do it? Is it possible for you guys? So what they said is that this is a charge q at a center, and around this charge one of the small charge, let's say small q, is moving in radius r, and to rotate this you need to find out the work done. Yes, so now you can assume that, let's say this is point a and this is point b. Now you need to shift this charge from q to b, from a to b. So when we have started this unit, that means the first unit of this lecture tells me that delta v should be is equals to work done by charge. So my work done should be is equals to VB minus of VA multiplied by Q. It's a VB minus of VA multiplied by Q. Now, what would be the potential? What would be the potential at point B? Yes, it is K Q by R minus of potential at A. Again, it is a K Q by R. Sorry, it would be n capital of Q. This is potential due to this charge. So this is kq by r multiplied by q. As this vb and va are similar, this work done required would be a 0. This work done would be a 0. Yes, yes. Let's look at the next question. What they said is that this figure shows some equipotential surfaces produced by some charge, at which point the value of electric field is greatest. Okay, we have three locations. One is the A, another is the C, another is the B. And what they want is, they want that value of electric field is greatest at which location. So what could you do? These are the electric field lines. Let's say somehow like this. These are the electric field lines. So as the properties of electric field lines, let's say these are the electric field lines and these are the uniform electric field. So if diagram is like this, then I may say that EA would be equals to EB would be equals to EC, because this is uniform electric field. But if diagram is something like this, this is location A, this is location B, this is location C, this is location D, at which point electric field is maximum. That in previous unit I have already discussed this, that when concentration of electric field lines are higher, electric field is higher at that location. So in this case, if I compare this A, C and B, two electric field lines are concentrated higher as compared to the C and A. So electric field is greatest at location B. Electric field is greatest at location B. Yes, yes. As I said previously as well, that first unit and second unit, they are related with each other. So to get a conceptually clarity of second unit as well, you must be through with the first unit. So I again and again request that please revise a first unit as well when and when you find the time. Yes, let's look at the next question. Yes, that is we already discussed. What they ask is that angle between equipotential surfaces and lines of forces. What is it? Angle between equipotential surfaces and line of force. Yes, it is 90 degree. Got it. You assume it correctly. Yes. So can you do this kind of logical questions? Yes. So before we go to the next numericals, let's first check it out the certain properties of equipotential surfaces. These are the properties of equipotential surfaces. First, that means they said that no work is required to move a charge from one point to another on an equipotential surfaces. That this practical we already did. That if you remember the previous questions, a first question was this is q and this is q. If I shift it from a to b, my work done would be 0, because this whole surface, this complete surface is equipotential, and as its surface is equipotential, we do not need to perform we do not need to perform any kind of work done to move this charge from location A to location B. Yes. Next, no two equipotential surfaces intersect, because if they intersect, there could be two direction of electric field lines at the same point, and this is not possible at all. That's why two equipotential surfaces can not intersect. Next, and very important, the direction of electric lines of force or direction of electric field is always normal to the element dl of equipotential surface. That means electric field line and dl, it's a direction of electric field and direction of electric lines of force, both are perpendicular to each other. The angle between these two is 90 degree. Yes. Next, what they said is inside a hollow charged spherical conductor the potential is constant. That I know. That this is the surface, and this is let's say a hollow cylindrical conductor, and let's say this is having a charge q. Then from this location, that means from center to the surface, its potential is k q by r. And so that as it is an equipotential surfaces, so no work done is required to move a charge from center to the sphere. But work done would require if it is a solid non-conducting sphere, because in the previous classes we have already seen this, that at center at center potential would be, what is it? Yes, it is 3 by 2 kq by r, and on the surface potential was kq by r. I am talking about the non-conducting sphere. Here this people are talking about the spherical charge conductor. That means they are talking about the conducting sphere. I hope these things are clear to you. Yes. So these are the properties. Yes. Now can you do the numericals based on the same? Can you? Let's check it out. What they ask is that let's say this is at V is equals to 50 volt. This surface is as V is equals to 40 volt. This is at 30 volt. This is at 20 volt. Separation between this all are 20 centimeter. This is 20. This all are in centimeter. This is centimeter. Yes. They want us to find out direction and magnitude of electric field. They want us to find out the direction and magnitude of electric field. So let's, at the initial stage, we are working on the direction, and then we will move to the magnitude of electric field. Now, what properties of equipotential surface tells me? What does it tell? It tells that direction of electric field is towards the decreasing potential. Now look at this. This surface is on 50 volt. This surface is on 40 volt. This is on 30. This is on 20. So my electric field should be look like this, in positive x direction. Yes, this should be the direction of electric field. So electric field is in, let's say, x, because I don't know the value at this point of time, is in electric field is in positive x direction. So electric field should be is equals to x of I cap. Now it's a time to find out the magnitude of electric field. Now, do you know any relation that relates voltage, or I can say potential difference, distance and electric field? Do you know any relation? Do you know any relation that relate potential, that relate a potential, electric field and distance? Yes. What is it? What is it? Yes, it is E is equals to, let's say here I'm interested in magnitude, so this is dV by dr. Then dV is the difference of potential. This is at 50 volt, this is at 40 volt, so this is 50 minus of 40, divide by separation between these two plates. It's a 20 centimeter, but this is in centimeter, that needs to be converted. So this is 20 by 100. I hope these things are clear to you. So this is mode of E. This is mode of E, that is 50 minus 40, it is 10, divide by 20 into 100. So this 25 is 100 and this is 50 Newton per coulomb or volt per meter. This is the electric field. This is the value of electric field. So what I can know is that electric field is equals to 50. Electric field is equals to 50 Newton per coulomb I cap. Yes. Are you sure? Can you do this? Can you do this? Will you? Okay. Let's do the next question. Let's do it. Suppose they said that this is one of the sphere having charge q, and this radius is r. Now let's say I make one more sphere here, and this is having a radius of r2. Let's say this is an r1. Now let's note the points somewhere. This is point A, here it is point B, here it is point C, here it is point D, and basically this charge has been put up at here. Basically this charge is put up at here. Yes, so please don't underestimate this, that this is having a two charges. We are having a single charge, and that charge is placed at the center of the spheres. Now what they ask is that find out work done require to move a point charge from A to B. Yes. So first tell me, potential at A, what is it? It's a kq by r. Potential at B, again it's a kq by r, because both are on same surface. Can you say this? As both are on same surface, work done should be a 0, because work done is equals to q into bracket vb minus va, and as this two are on the same surface, the difference would be a 0. So this is work done would be a 0. This was just the first property of equipotential surfaces, that to shift a charge from one location to another location on a equipotential surfaces, work done required would be zero. Have you remember this? Do you? Yes, great. So this work done would be a zero. But let me ask one thing, that if if a question has been asked, if a same question has been asked, such that find out work done require to move a charge from point A to C, what was your answer? Is it 0 or non-zero work done? Is it 0 or non-zero work done? So how can you get an answer that whether it would be a 0 or it would be a non-zero? You need to simply perform this. Work done is equals to Q from A to C. So this is potential at C minus potential at A. Now what is potential at C? Potential at C, it is KQ by R2, and potential at A, that I know, KQ by R, as both this are non both this are two different potentials, so this should not be equals to 0. And what it would be, that you can definitely calculate, that potential at C, potential at A, subtract it and multiply it with the Q. So I hope these things are clear. This surface, a surface which includes C and D, this is equipotential surfaces. This complete surface is equipotential surface. But you cannot say that B and C are the equipotential surfaces. They are two different surfaces, because these two surfaces are having a different potentials, and if their potential is different, they cannot be considered as an equipotential surface. Clear? Are you clear with this? Are you sure? Are you sure with this? So let's move to the next question. What they asked? They asked us that four equipotential curves in an electric field are shown in the figure. That and A, B and C are the 3 points in the field. Okay. If electric intensity at A, B, C are EA, EB and EC respectively, then okay, you need to find out that which electric field will be higher, which would be a lower, and you need to arrange them accordingly. So this is 120 volt, this is 90 volt, this is 60 volt, this is 30 volt. Now how could you get an instinct that which one or which electric field will be higher, which electric field will be a lower? How could you manage it? First look that this all surfaces are having approximately same separation, let's say x. Yes. And what you need to do is you need to simply put up a value of E is equals to dv by dr. E is equals to dv by dr. Yes. So if I put this, what I get is that, because 120 minus 90, 90 minus 60, 60 minus 30, all are separated by 30 volt. Yes, all are separated by 30 volt itself, and their separation looks equal. Look at this separations. The separations are look equal. So their dv is equal, their separation is equal, so their electric field must be equal. So this could be the answer. Their electric field must be the equal. Yes. One more question. Shall I add to this? Shall I add to this one more question? What would be the direction? What would be the direction of electric field? What is it? Direction of electric field. Yes, it is towards the decreasing potential. And when I assume and when I want to find out the decreasing potential, it is 120, 290, 260, 230. This is in positive x direction plus I cap. This is direction. This is direction of electric field. We cannot have an exact value because we have been not provided with the data of an x, but we know that this is, or this electric field is in the positive I cap. Yes, you understand this? Are you sure? Can you do this kind of question? Will you? Okay, let's look at the next question. A very good question. What they ask is, go through this. Some equipotential surfaces are shown in the figure, and what they say is, what can you say about the magnitude and the direction of the electric field? They ask us that what can you say about the magnitude and the direction of electric field. So what you should do at a very first stage, what you should do at a very first stage, look at this. These are the surfaces which are on same potential. Let's say this is first, second, third, fourth. Yes, these surfaces are on a same potential, 280 volt, 220. So their difference is of 60 volt. Even here from 220 to 160, it's a difference of 60. Even 160 to 100, even this is a difference of 60 volt. So this all voltages are at this all voltages are at difference of 60 volt. Now what you need to find out, you need to find out the magnitude and direction of the field. So so do you know what is the direction of electric field? Yes, direction of electric field is always towards the decreasing potential. That I know. Direction of electric field is towards the decreasing potential. So if I assume it's a 160, it's an 100. So if I make a one of the line, then this is this must be the direction of electric field. Look, something like this. I hope these things are clear to you. One more observation you must make at here is that electric field, this is electric field, direction of electric field must be perpendicular to the must be perpendicular to the equipotential surface. So this should be the direction. Yes, it just makes an angle of this much with x-axis. We are just calculating this, but before we calculate that, do you have a clear cut idea of this? Yes. Do you have any doubts up till now? Do you have any doubts up till now? Is there anything? No. So let's calculate this. Look at this. This is 160, this is 100. So this should be the direction of electric field. Yes, this should be 90 degree. This should be the 90 degree. This is 37. This is 37. So if it is 37, this is 90, and this should be this angle should be having a value of, what is it? It's a 53 degree. Yes, it's a 53 degree. And the separation, this separation is 10. What I am looking forward is E is equals to delta V divided by delta R. Working on the magnitude, E is equals to delta V by delta R. So what I can assume and what I can feel is that I need to find out this distance, that this point is A. I hope these things are clear to you. And this is B. I need to find out the distance between A and B. If it's a very clumsy, let me draw it. That this is, let's say, point C, and this is the situation that B is at right angle triangle. Let's say this is C, this is A, and distance between C to A, distance between C to A, it's an hypotenuse, it's a 10, and this angle between BC and CA, this is 37, so this is 53 that I know. And you are interested in AB, you are interested in AB. Now tell me, you are interested in this AB, how can you do this? How can you do this? So what I can assume is, or what I can see is, that for this triangle, if I write a value of sine 37 degree, what it would be? Sine 37, it's an AB divided by AC, that means it's a 10. So AB would be is equals to 10 multiplied by sine 37. Now again the question arises, what is the value of sine 37? What is the value of sine 37? I am sure you must know the magic triangle, you must know the magic triangle. But if you note, but if you don't know magic triangle, then look at this. This is the magic triangle. This is 3, this is 4, this is 5. This should be a 90 degree. 3 and 5, angle between 3 and 5 is 53 degree. Always remember this, that 3 angle between 3 and 5 is 53 degree, and so this is 37 degree. If you remember this triangle, then from this you can have a exactly idea of sine 37. What is it? Yes, it's a 3 by 5. So this is 5 2s are 10 and 2 3s are 6. That AB is 6. Yes. So now let's put up the value. It's a delta V. Delta V, it's a difference of potential. This is 160 volt, this is 100 volts. It's a 160 minus of 100, divide by delta R. Delta R is the distance. That distance is 6, but this is in centimeter, so it's a 6 multiplied by 100. So if I solve this, this is 160 minus 100, so this is 60 by 6 into 100. This is 6 tens are 60, and this is equals to 1000 Newton per coulomb. It's a 1000 Newton per coulomb. Yes, yes. Are you done with this? Are you? Yes. Now, uh, last, what would be the what they ask? They ask about the magnitude, and one more thing. They also want the direction of the electric field. Now, what is the direction of electric field? Look at this. This was 37. This is 90. So this is 53. This angle is 50. This angle is 53 degree. So what is this angle? What would be the value of this angle? What is it? That should be 150 minus of 53. That means 150 minus of 53. What is it? Yes. What is it? It's a 137. Yes, it's a 137. Sorry, this is 180 minus 53. My mistake. It's a 180 minus 53. So it would be an 137. So I can say that electric field makes an angle of 137 degree with x-axis. Yes, electric field makes an angle of 137 degree with the x-axis. I hope these things are clear. So shall I repeat this? Shall I repeat this? What should I do is, what should I do? First, I need to find out the direction of electric field. Direction of electric field can be easily calculated by knowing that fact that direction of electric field should be towards the decreasing potential, and my decreasing potential is in this direction. Then I must know that what is E is equals to. I know that E is equals to delta V by delta R. So just put up the difference of the potential between two equipotential surfaces and find out find out separation between them. But when you find out the separation between these two surfaces, you must know that separation should be perpendicular to them, because they have already given 10, but this distance is not perpendicular to them. This is not perpendicular to the 100 and 160. So that's why I need to find out the perpendicular distance. That perpendicular distance can be easily calculated using simple trigonometry, and then E should be is equals to delta V by delta R. I hope these things are clear. Is it? Any doubts? No? So let's wind it out here. Yes, in this class we were discussing about the equipotential surface, a very shorter amount of topic, but this unit and this topic has a capability to give a questions in competitive examinations, and many are times this unit contributes one or two questions in NEET examinations as a JE examination. So please go through this, go through class notes and do as many questions as possible. So let's sign off from my side. Thank you. Have a good day. Take care.